All right, back from break. A lot of good stuff in that first hour. Let's see what we've got left in the rest of the chapter. So this again, this is like the really physics stuff that we're getting into, because now we're looking at forces and how they create accelerations and how velocities and displacements will be related. So now we want to talk about the force of gravity, and we said right up front earlier in the chapter, this is basically it. The gravitational force, F equals mg. The book is going to call this weight. I am not. I'm going to stay away from the word weight. We'll talk more about that in some examples, but I'm just going to refer to this as the gravitational force. And again, these are two distinct properties of mass. Mass determines how much inertia an object will have, so that helps determine how much acceleration there will be. And then property 2, gravitational, mass determines how large the gravitational force will be. Apparently the same mass works with these two very distinct properties. Now this is referred to, I keep calling it the gravitational field. I think the book is calling it the gravitational acceleration. I'm going to start playing around with some different units here. Instead of using meters per second squared, I'm going to write little g, the gravitational field, as 9.80 newtons per kilogram, and I'm going to call it the gravitational field. So the newtons per kilogram is reminding me that this is how I actually use little g. Little g is used to determine how large the gravitational force will be. It just happens to have units of acceleration to it. All right, so here's an object. Now, in order for the object to be at rest, let's see, at rest is one of those examples of constant velocity. So being at rest is this, I've got it highlighted, is the same thing as constant velocity. That means the acceleration is 0. If I have an example like this, I'm given a problem where I have an object and there's no acceleration taking place, then I know that the normal force would have to match the gravitational force. And that tells me that N equals mg. Now, again, here are the two properties that we're thinking in terms of. I guess I should reverse these slides. This is what I was talking about before. Property number 1 is the inertial property. And that is used in this formula, which I'm going to say, if there's one formula that we would say is representative of the entire course, one formula we're going to use more than any other formula or come back to as kind of a foundation for all of the analyses we do, it's this. Okay, and that includes the inertial mass, and this is the diagram. The gravitational formula, F equals mg, that's just telling me how to determine gravitational forces. Now, gravitational forces do tend to show up in pretty much every example that we look at. And when they do, we can just write them as mg. Okay, so let's try this mysterious box. This, for better or worse, this box is going to follow us through this chapter and the next chapter. So we have a box. It's got a gravitational force. It's got a normal force acting on it. We're going to start off just setting it on a table. And then we're going to push down on it with 40 newtons and ask what happens to the gravitational force, what happens to the normal force. And then we're going to lift up with 40 newtons and ask what happens then. Now the box, they tell us, has a mass of 10 kilograms. So let's see what happens with these three different cases. So let's first of all be clear, when we first set the box on the surface and there's no acceleration taking place, it's at rest, it stays at rest, there's no acceleration. The mass is 10 kilograms. That means that the gravitational force is 98 newtons. Now let's think about the kind of the sequence of reasoning here. If the mass is 10 kilograms, then the gravitational force, which is mg, would be 98 newtons. How do we determine what the normal force will be? And the normal force is going to come from saying, when it's just sitting there, the acceleration in the y direction is 0. The two forces in the y direction are n and mg. If the acceleration is 0, the F net has to be 0. Those two forces must balance out. Since we know how large the gravitational force is, it says that the normal force in this circumstance needs to match the gravitational force. So the normal force also must be 98 newtons and needs to be equal to mg in the first example. So that's just the first example. Now what happens when you come in and you push downwards with an additional 40 newtons? So we're pushing down. Well, that doesn't change gravity. Gravity stays right at 98 newtons. The box's mass has not changed. The Earth's gravitational field has not changed. And so it's going to be the same. The Earth's gravitational field is still 9.80 newtons per kilogram. When I multiply that by 10 kilograms, the kilograms cancel, and I'm left with 98 newtons of gravitational force. That's going to stay the same throughout the problem. Now, in this case, what we would say is the box is going to stay with no acceleration. It's going to stay at rest, and more than just being at rest, it's going to stay at constant velocity, which says there will not be an acceleration. So in this case also, the net force needs to be equal to 0. Now this time, when I look at the net force, I've got N upwards, I've got mg downwards, but I have an additional downward force. So the normal force now, the contact force along the tabletop, needs to be equal to mg plus F. So when we push down with 40 newtons, the normal force is going to go up. It's going to rise to a value of 138. Now in the last example that they've given us here, we're going to be lifting up. So I'm going to call this tension in some kind of a rope, I guess, that they're lifting, or a string that they're lifting this up with. Again, what's going to happen is they tell us, is this true? Do they tell us the box does not come off? Ooh, not necessarily. So there's a couple possibilities here, and I'm guessing you guys are already thinking, you're probably ahead of me on this. If that tension is large enough, it's going to come right off the table. If the tension is large enough, it will come off the table. The normal force will be 0 if that happens. If it's no longer in contact, the normal force is going to be 0. Let's see. What I'm going to first of all assume is that it doesn't come off the table, and let's see how that works. So let me assume that it remains on the table. If it doesn't, I think our calculations will show that. So what we're going to have is A is equal to 0, the net force is equal to 0. This time, if I look at my force diagram, N plus T together are upwards, mg is downwards, and if there's no acceleration, all the upward forces are being balanced by all the downward forces. Now I'm specifically interested in solving for N, and so that's going to be mg minus T, and that gives us 98, so the normal force is 58, and that tells me that yes, it will stay on the table. Lifting upwards with 40 newtons will not be enough to offset the 98 newtons from gravity. So at 40 newtons of lift, the normal force will be reduced, but it's not going to go away. It's going to stay in contact. Okay, I hope that all made sense. So any questions on that? All right. Let's move on. Now, what would happen if we did this? What if instead of lifting with 40 newtons, what if we lift with 100 newtons? So now we're going to lift with 100 newtons. Remember the gravitational force we calculated, mg, it's only 98 newtons. So the force upward, the tension in the rope, it's enough now that it could, and it will, offset the gravitational force. what will happen? So what we're expecting is this thing now lifts off the table. What will the normal force be? Normal force is 0. So the normal force is 0 now. So our force diagram now has gravity. It continues to have gravity. It continues to have tension, but the normal force is gone. Remember, the mass was 10 kilograms. Gravitational field, 9.80 newtons per kilogram. Kilograms cancel. mg, the gravitational force, is 98 newtons. The tension we're pulling with is 100. That means that the net force in the vertical direction is 100 minus 98. Now, assuming this is 98.0 and that's 100.0, this would give us 2 newtons of upward net force. So the net force will be upward, but it's only 2 newtons. That's not much. So let's calculate the acceleration that we're going to create from this. We're going to kind of repeat what we just did. Sum all the forces together, divide through by the mass. Summing the forces together means taking t and subtracting off mg. The acceleration direction we're going to get is upwards. I should have an acceleration symbol right there. So I should have put that in. I should have drawn in an acceleration off to the side. T minus mg left with 2 newtons of net force. Now the inertia is 10 kilograms. So 2 newtons acting on 10 kilograms of mass will give us an acceleration of 0.20 meters per second squared. So that's what we're going to end up with, is we're going to end up with an upwards acceleration, 0.20 meters per second squared. And this example shows the 2 properties of mass. This m is a gravitational effect. This m is the inertial effect. So they're both present in this example. Okay, here is a person in an elevator. The woman here is 65, her mass is 65 kilograms. She is descending in an elevator, and it briefly accelerates downwards at 0.20 g. And she's going to stand on a scale that doesn't bounce around. We're going to stand on a scale that very accurately tells us the normal force. Scales are measuring normal force, so let's be clear about that too. There's a gravitational force acting on the person. There is a normal force, and the normal force is coming from the springs, from the scales that she's standing on. So when I stand on a scale, the scale's measuring a normal force. Now, when we stand on a scale and measure our weight, measure the gravitational force, we're assuming that we're not accelerating upwards or downwards at the time. And for that, n will equal mg. During this acceleration, what is so during this acceleration, what will be the gravitational force and what will the normal force be? Now, this is one of those examples where we run into a little ambiguity here. What is her weight? Is her weight the gravitational force mg, or is her weight going to be the normal force, which is probably going to be a little less, right? If we're accelerating downwards, let's take a look at the force diagram and see how that works. So here's the object. Here are the forces acting on the object. There's an mg and there's an n. Now there's an acceleration taking place, and because there is an acceleration, that tells us that n and mg are not the same. In fact, it tells us that if we have an acceleration downwards, it must be that the normal force is less than mg. If n equaled mg, we would have no acceleration. To have an acceleration in this direction, n is going to be less. Now, we can, first of all, take their numbers. They said the acceleration will be 0.20 times g. So I'm going to take 0.20 times the 9.80. Now, I went back and used meters per second squared here because we want to be able to get an acceleration set of units for this. So the acceleration here works out to be 1.96 meters per second squared. That's going to be downwards. Now, what I'm going to do then is since I'm writing the acceleration as being downwards, and I don't want to introduce a minus sign if I don't need to. So since this is my positive direction, then mg is in the same direction as the acceleration. That gets a positive sign. Now the normal force is opposing the direction of acceleration. That gets a negative sign. So mg minus n. Now I've got to divide the whole thing by the mass. That's the inertial factor. And when I do that, I get a formula that says n equals mg minus ma. So it says that the normal force can be determined by calculating the gravitational force and subtracting off the mass of the object times the acceleration. The force will be reduced by an amount related to the acceleration. And that says that the normal force is only 510 newtons. So again, this becomes a question, what's her weight? Is her weight the 637 newtons that we calculated from the gravitational force, or is her weight what the scales are reading, which is the normal force of 510? And that's why, I mean, I don't mind using the word weight. We just have to, if we're using the word weight, we have to be clear, are we referring to a gravitational force, or are we referring to the normal force? Because it gets used back and forth. You'll probably notice that. Reading the textbook in examples, it kind of switches back between the two. Now, what that would be the equivalent of, if the person's measuring themselves in kilograms, what would the scale read? So the scale is designed not to read in newtons, but rather to read in kilograms. So I can take this normal force and divide it by the gravitational field to find out what would be the equivalent mass that would create a force of 510 newtons. The mass that would create a gravitational force of 510 would be 52 kilograms. So that's a pretty good acceleration, right? It's like 1/5 of gravity, and so the scale is going to respond with saying that the mass appears to have decreased by a factor of 1/5 reduced. So we're down to 80% of what the scale read before. Now, of course, the mass hasn't changed, but it's an acceleration effect that's showing up with the scales. Okay, another good example. Now, what would happen then once the elevator hits cruising speed? So if you've been in an elevator in a really tall building and the elevators have to move pretty quickly, what they do is they have a pretty, good-sized acceleration for a short time, and then they just cruise. And so this thing is cruising at a pretty good speed, but it doesn't matter, whatever speed it's cruising at, if v is constant, a is 0. And that means that the net force is 0. So to cruise at a constant speed, the normal force and mg will go back to equaling each other. So now the normal force will be equal to mg, 637, and the scales, I can take the normal force divided by g to find out what the scale reads. The scale goes back to reading 65 kilograms. So constant velocity doesn't require a net force. The forces in this case are balanced, and that results not in being at rest, but being at constant velocity. Okay, so you got to keep reminding yourself that when the forces all cancel out, the object continues traveling at constant velocity. If it's at rest, it continues to be at rest. All right, and so this is just an example of adding forces. We've been doing this, well, maybe not so much. Maybe this is good. So what we're going to do now is we're going to take these two forces. I was going to say that we've looked at components, but we really haven't. So this is our first look at taking a force and dividing it into components. Hopefully you guys remember from chapter 3, we did this with displacements, we did this with velocities. I don't know if we did it with accelerations, but we can. So any vector can be divided into components. And so what we're going to do is look at some forces This force is acting at 45 degrees, this one's acting at 37. And what we can do is draw a free body diagram. So the object we're thinking in terms of is that boat, but we're really more specifically right now just looking at two of the forces. We're not looking at all the forces acting on the boat. The tension here and the tension here. And what that diagram is showing is that each of those forces now needs to be resolved into components. We need to divide it up into x and y components. Now when we do that, this lower diagram is showing what happens. And so what happens here is the two x components are working together. So I'm going to get a cosine 45 portion of this force. I'm going to get a cosine of 37, and those are both going to apply to the x direction. So I'm going to get those two x components added together. When we add them together, this is how big they are. When I take the y components, the ones that are sideways, one of the sideways components is bigger. So the two forces are not, these two angled forces are not going to pull the object directly forward. Instead, they're tending to pull the object to one side. Maybe that's the side they want to bring the boat in and attach it to the pier on that side. In any case, the net effect of those two forces is going to have a certain angle to it. I think we've done this with other vectors, so let's take a look at this one. Same diagram as we saw before. I'm calling this theta 1, I'm calling this theta 2. Now, if we look at all of the forces in the x direction, I'm going to get force A, which it tells us is 40 newtons, times the cosine of angle 1, and the angle is given as 45. Force B is going to have an x component that is FB cosine of theta 2. That's 30 newtons at an angle of 37. So what we've done so far is combine this component and that component. So those two components together are going to determine how much force we have in the x direction. Doing all the math, I get 52.2 newtons. Now, in the y direction, what's happening is these are opposing each other. The y component from force A and the y component from force B, the two sideways forces, are opposed. And so here, looking at my diagram, I'm going to leave a plus sign on one of these, but I'm going to put a minus sign in to represent what's going on in that lower quadrant. And so this gets, so the minus sign got dropped here. That needs to be a minus sign. Get that written in. So I'm taking the magnitude here, subtracting off the magnitude of this side, and I'm getting a net force of 10.2 in the positive direction. And so that's that's a very good example of going back and looking at adding force vectors together, which we're going to be doing a lot. Okay, adding force vectors together is really, really important. Okay, let's take a look at this example. Oh, I have to look at this just a little longer. Okay, there are two forces, and we're combining those two vectors together to find out what the net force will be in the x, net force in the y. All right, here is a hockey puck. It's sliding along the ice. It says that the ice surface, we are going to assume the ice surface is frictionless. I know we just say that, and it makes it so in physics. So there are not very many examples of truly frictionless surfaces, right? Anyway, this ice surface is just 100% frictionless, and so the motion here is, it says that the puck is moving at a constant velocity and that there is no frictional force, which is the correct free body diagram. So V, they're calling it motion, which is a little vague. I'm going to say this is the velocity vector is here. That is velocity. This is the velocity vector. This is the velocity vector. Here's the normal force, here's the gravitational force. Those are going to be equal to each other in magnitude. And we don't need any forces. So I think the one in the middle is the correct one. We do not, if there were a force in this direction, in the direction it's traveling, it would go faster and faster. If there were a force here, it would be slowing down. Now, in reality, ice does have some friction, and so this is what would really happen in reality. But if it's truly frictionless ice, the force diagram would not contain any frictional force. It would be maintaining constant velocity because there are no forces acting on it. All right, here is the mystery box again. I thought it had gone away, but it's back. Let's see, it's still 10 kilograms. And now what we're going to do is we're going to take that 10 kilogram, it looks like an envelope, but I guess it's a box, so it's got some depth to it. Here's the 10 kilogram box. This time we're going to pull on it with a force of 40 newtons, but we're going to pull on it at an angle. So we're going to try using these different force components to see what's going on. So let's try that. So the free body diagram, or the force diagram now, looks a little different. What we've got is the mass is here, the object is here. The force now, which I'm calling tension, is at an angle theta. There's a normal force and there's a gravitational force, and the surface, did they say it's frictionless? I'm sure it's frictionless. We don't really take a close look at friction until chapter 5. So for now, it says it's a smooth surface of a table. Yeah. So they're claiming, probably unreliably, that there's no friction here, so we'll go along with that. So the forces we have then are we have mg and we have n. And we have this new force of tension. Now, mg we've looked at, that's 98 newtons. And is the normal force going to be 98 newtons this time? Because the tension force is at an angle, and that means the tension force we are going to resolve into components. We're going to have a t sine component and a t cosine component. Here is the t cosine, here is the t sine. The tension is 40 newtons at 30 degrees. When I look in the x direction, I'm guessing there's going to be an acceleration. There's just got to be, because t cosine is in the x direction and there's nothing opposing it. T cosine is running unopposed, and so the net force in the x direction is t cosine theta, and we have to divide through by the 10 kilograms, right? So divide through by 10 kilograms, the t cosine theta divided by 10 leaves us with, that's a pretty good acceleration. 3.46 meters per second squared is the acceleration that we're going to be getting as a result from that. Now, for part B, what we want to do is take a look at the normal force. I'm guessing the normal force is going to be reduced because the normal force by itself is not offsetting gravity. There's this extra t sine theta. Now again, you guys are probably thinking, hey, if I pull at an angle enough, I could still lift the box off the surface. So we're going to have to double check and make sure that we're not lifting the box off the surface. So let's try this. For part B, we're going to start by assuming it doesn't come off the surface. There's no acceleration in the y direction. So if that's the case, then the forces in the y direction add up to be 0. So that means I can take all of the vertical forces up and set them equal to all the vertical forces that are down. That's n plus t sine theta equals mg. And that tells me that the value of n would be mg, but reduced by t sine theta, and that leaves us with 78 newtons. So the normal force is different. That's interesting. That's something you want to be able to go in, understand, carry out these calculations. So with all these examples, You should be able to do the example and then set your work aside, come back the next day, get out a fresh sheet of paper or something and work through the example. Each time you go through, you should be using fewer and fewer, you should require less and less assistance until you get to a point where you look at the problem and go, yeah, I know how to do that. And it's not so much that you've memorized one particular type of problem, but rather that what you've done is you've learned what are the principles behind setting the problems up. So you definitely want to be in a situation where if a new problem gets thrown at you, you can solve the new problem. That's the goal here, right? All right, so we got the acceleration determined, and we got the normal force figured out. Oh no, there's two mystery boxes now. All right, so we've got these two mystery boxes. I kind of liked when they're just one. Anyway, we got two of these, and the two boxes combined are being pulled to the right with 40 newtons. So this is box A, this is box B. This one's 10 kilograms. Oh, this one is massive. Look, it's got 12 kilograms of mass. So 10 kilograms for one, 12 kilograms for the other. And the string in between, we're saying the string has got a tiny, tiny mass. We're not going to be concerned with that. And so what we can do is draw a force diagram combined for both of them. And then we can go in and draw individual force diagrams. Now, right here, they're showing the individual ones. So let's take a look at what they've drawn. It looks so nice. So for object 1, object A, there is a normal force and there's a gravitational force. There is a force of being pulled forward and there's a force of being pulled backwards, and that's coming from the tension in the string. So notice we have isolated this object. We could have treated them as one, but right now we've isolated that and drawn this diagram. So normal force, gravity, force of the pull, and then the tension. Now, that's what the force diagram looks like. If we now move on to box 2, box B, this also has a gravitational force, and it has its own normal force, and it has a tension of the string. Now, the tension pulling back on object 1, object A, is the same as the tension pulling forward on object 2, or object B. Those two tensions are going to be the same, and that's because we assumed this string has very little mass. And so if I imagine myself to be the string is being pulled forward by this box, the string is being pulled backwards by this box, and the net force here for the string itself doesn't need to be, we don't need a net force. It doesn't have much mass. We're just going to assume those tensions are essentially the same value because the mass is so small. So Ft here is going to match Ft here. Now, is there anything that I misread? Because I need to pay attention to reading the problem. So we need to find the acceleration of each box, and we want to find out how much tension there is in the string. Now, notice the way the boxes are configured, they don't have individual accelerations. They're going to have the very same acceleration. There's not two accelerations we're solving for. It's just one, and that one acceleration will apply to both. So I'm suggesting this. I'm suggesting that in addition to the individual force diagrams, the free body diagrams, let's draw one that treats both objects together as one object. So I'm going to take the one object approach. Now when I take the one object approach, how much mass does the one object have? And the one object approach says we have one object with a mass of 22 kilograms. Now that one object is being pulled to the right by 40 newtons. What about the string in between? You go, no, it's one object. There is no string in between right now. So I don't have to concern myself with the tension because the tension is acting between individual parts of my object, and I'm treating both combined as one object, so the effects of the string go away. Now I do have to include N1 and N2 get combined into an overall normal force, M1G and M2G get combined into an overall gravitational force, and the acceleration will be given by the net force, F, divided by M1 plus F. There's no friction. So we'll see this. I'm sure this mystery box is going to come back in chapter 5 when we look at friction. I just don't think it's going away. So we're going to have 40 newtons of net force pulling on M1 plus M2 combined into 22. The acceleration is going to be 1.82 meters per second, and that's going to apply for both of these objects, not just one of them. All right, so for the acceleration, we use the one object approach. Now, when they ask us about the tension in the string, I have to go take the two objects approach, because when I did one object, the string wasn't even there. It was just part of the object itself. Now when I separate it into two objects, the tension in the string shows up. Now remember, the tension pulling back on object 1 and pulling forward on object 2 is the same tension. I don't have to solve for two tensions, I'm just solving for one. So what I can do is for object 1, I can take the acceleration that we've determined here. I can set that equal to F minus t, divide that through by m1. Remember, it's isolated now, it's just the mass m1. I could use that to solve for the tension. Or I could solve for the tension here. I could say that let's just focus on object 2 and say the acceleration of object 2 is equal to the net force, which is t, divided by m2. That's even easier. That doesn't have two forces, it just has one. Either one of those should give me the same value for tension. Okay. Now there's a third way we can operate, so let's see how this works. When I went through and solved the equation based on the diagram for object 2, what I found was that m2 times a, that tension would need to be 21.8 newtons. When I took a look at the formula from object 1, I got F minus m1a, and that also worked out to be 21.8. So this is a way to double check your answers. So if you want to check and see if your answers are all consistent, you can solve for both of these and see if they match up. Now there's a third way that we had hinted at, and that would be to say that the acceleration of object 2 equals the acceleration of object 1. The two accelerations are the same, and that means that down here, ax is equal to t over m2, ax is also equal. I've got two separate equations of ax. I can set those equal to each other, and that would give me t over m2 is equal to f minus t over m1. Now, why would I want to do that? There's a couple of reasons here. The first reason is, let's imagine that when they asked me to solve the acceleration, I got it wrong. What if I got the acceleration wrong? What's going to happen in the problem? Well, if I got the acceleration wrong, then these answers up here will also be wrong. This gives me a chance to start over again and see if I can get tension right, even if I got acceleration wrong. Now, of course, if you're doing homework, you want to use every approach you can and see if they keep giving you the same answer. And that's telling us that algebraically they're all equivalent. Algebraically, we've got some number of equations we're working from, and at the end of the day, they have to all give us the same answer. So using this approach, and then doing some cross-multiplying, solving for t, I ended up with m2 over m1 plus m2 times the force. I put those numbers in, and I got 21.8, but let's take, which matches, so that's good. But let's take a look at the algebra that we're looking at here. And that is, notice that by using this approach, I learned something from the algebra. What I learned was that the tension in the string holding the two blocks together is a certain portion of the force that's pulling them both. So the idea is force F because of the way the strings are hooked up between the boxes, force F is basically pulling on both of those boxes. Not directly, in the force diagrams that wasn't it, but we needed this force to create the acceleration for both. How much tension then is going to get set up? And the tension is going to be related to the total force by the ratio of how much of the mass is in the second box. And that worked out to be 0.545. Now, if the two blocks had both been 10 kilograms, what this is saying is that pulling 10 kilograms compared with the total 20 would require the tension to be 1/2. It's not exactly 1/2. Instead, it's 12 kilograms out of 22 that the tension has to provide for. But again, carrying out the algebra and then staring at the formulas, you can learn things. You can learn something about how this is all going to be operating. Okay, I think we've got one or two examples left. I think we're pretty much on pace here. Here we have an elevator at 1,150 kilograms, and we have a counterweight at 1,000 kilograms, and we've got it going over a pulley. Now we're going to ignore the mass of the pulley, we're going to ignore the mass of the cables, we're going to ignore any friction in the axle. And so what that says is that the counterweight and the elevator each are going to have two forces acting on them. And there's going to be a tension pulling up on the elevator, and there's going to be an mg downwards on the elevator. The counterweight, there's an mg downward, there's a tension up. Now, these two tensions are the same, and they're the same because, again, we're assuming the cable has very little mass and the pulley has very little mass, and that there's no friction involved in the pulley rotating. So that's not going to contribute to differences in tension. So these two tensions are going to be the same, and what they want to know is what's the acceleration of this system, and what happens with the tension in the cable. So the elevator itself is 850 for passengers. I don't think that's going to be a problem here. Okay, so I think everything we've looked at, let me see if I can, okay, so I drew it like this. Here's a couple of pulleys. Here is the counterweight, M2. Here is the elevator, M1. M1 is equal to 1,150 kilograms with 4 passengers on board. M2 is 1,000. For object 1, which is the elevator, we're assuming the acceleration will be in this direction because M1 is bigger than M2. So M1G is going to be bigger than M2G. That's what's going to happen in this example. And so I'm writing the acceleration in this direction. Now the counterweight is going to have the very same amount of acceleration, the very same acceleration, except the direction is opposite. So I'm going to draw this as a force diagram for object 1, and then a force diagram for object 2. And for object 1, M1G, is in the direction of the acceleration. I can subtract off the tension, divide by M1, and that's my formula for calculating the acceleration. Now, I'm kind of looking ahead, thinking I'm going to also need to calculate the tension. And so I wrote it both in terms of the acceleration, and then I wrote it in terms of the tension. Now for object 2, what I'm going to do is also write down the very same formula, but remember, acceleration is in the opposite direction. So this time, T gets the positive sign, M2G gets the negative sign. This is what the acceleration formula looks like. This is how the tension is related to the forces and the acceleration. So I'm going to take these two formulas, these two lower ones, where I've solved for tension, and I'm going to set those equal to each other. Since I've got two formulas, T equals this and T equals this, I can take the two and set those equal, and then collect terms, solve for A, and the formula that I ended up with, again, it's algebraic. I'm not putting the numbers in right away. I'm holding off on that because the formula is going to tell me that the acceleration depends on the mass of the two objects, the gravitational field, and again, the mass of the two objects. Now, up here are the gravitational forces. So the net force driving this system is going to be m1g minus m2g. The inertia is going to be m1 plus m2. So at the end of the day, I could have created this, set this up as if it were one object. And it's one object being pulled with m1g here, but being opposed with m2g here. The net force is m1g minus m2g. And then the inertia in these two objects is m1 plus m2. So I guess I could have treated it as one object and just written down that formula. It's good to see how all the individual steps work. It's another good example, I think. I think the slides here have a lot of really good examples for them. Now, so I'm going to put the numbers in now. We talked about the formula we came up with for the acceleration. Let's put all the numbers in. The m1 minus m2 is 150 kilograms. Combining the two inertias gives us 2150 kilograms of inertia, and then I got to multiply by the gravitational field. So the acceleration works out to be 0.0698 times the gravitational acceleration. So that's about 7% of the gravitational acceleration, and that worked out to be 0.684 meters per second squared. Now they also wanted to know about tension. Now tension, by looking at the diagrams and looking at the accelerations, what we know, first of all, to start with, is tension is going to be less than m1g. Let's go back and look at that diagram of what's going on here. Tension is going to need to be less than m1g because there is an acceleration, but tension is also going to need to be bigger than m2g because of the directions of the acceleration. So what I'm looking for in my answer is m1g is 11,270 newtons. That's the gravitational force acting on the elevator. Here is the gravitational force acting on the counterweight. The tension's got to be intermediate to those two values. So I set the two formulas up. I actually took the acceleration formulas, set them up, and then carried through the algebra. And I ended up with a tension formula that is 2 times m1 m2 over m1 plus m2 times g. When I looked at the combined, the number, I put all the numbers in, took a look at all the units. I ended up with units of newtons for this, which we knew they had to be. And the number worked out to be 10,480 newtons. Now what I'm doing is I'm going back and checking my answer. Is that a reasonable answer? Well, for this particular force diagram, I knew that the tension would need to be intermediate between 11,270 and not necessarily right in the middle, but it needed to fall within those numbers, and it does. Okay, these are two very similarly, objects with similar masses, and the tension is coming out to be kind of intermediate, kind of in the middle of those mg values. All right, we're coming up on time here. I think we might go over just a few minutes, but there's a very important set of examples that we want to, or an important example we want to look at, and that's working with objects on inclines. And so if I've got the mystery box now on an incline, they're giving me some kind of an angle. It's 30 degrees. So it looks like the angle is 30 degrees. The mass is 10 kilograms still. When I do the force diagram here, I've got the normal force. Normal force is tipped. So that's something new. The gravitational force, though, is going to continue to be downwards. Now, should I use a coordinate system where horizontal and vertical, x and y are horizontal and vertical, or should I tip my coordinate system? So when I'm on an incline, the motion, the accelerations and the velocities, I should say, the displacements, the velocities, the accelerations are going to be along the incline. And what that lets me know is that I probably should pick a coordinate system that lines up with the incline. So I'm going to tip my coordinate system. I'm going to put x along the axis. I'm going to put y perpendicular to that. That means that in my force diagrams, when I take a look at the force diagrams that I have for this, the force diagrams, here is the object. I'm going to rotate the coordinate system. Now when I rotate the coordinate system, pay attention to where the angles show up. In order to get an incline of theta, I've got to take the x-axis and rotate it. Well, that means that anything, the y-axis, that means that the y-axis, which used to be vertical, is also going to be rotated through an angle theta. So theta shows up here, theta shows up here, theta shows up here. When I get to my force diagram, N is right along the y-axis. We rotated the y-axis, and there it is. The acceleration is right along the x-axis, and that was our intention. We wanted the acceleration to be exclusively along one axis. And so the acceleration is along the x, N is along the y. mg now is going to have to be resolved into components. Now remember our rules for taking a vector and dividing it into components. The vector needs to be surrounded by a rectangular box, and the rectangular box needs to be rotated so that it matches the x and the y axes that we're working from. So the rectangular box is rotated. The vector needs to be the diagonal through that rectangular box, and it is. So the way we've drawn it here is all the sides of the rectangle are tipped now by that angle theta. This is a really important set of diagrams. So make sure you're really clear about that. What it leaves us with is an mg sine theta directed along the incline. That's what's going to give us the acceleration. And then there's an mg cosine, and that's going to be now set up opposite to the normal force. So the normal force in mg cosine theta will be in opposite directions. So in the parallel direction, in the x direction, I should have said x. So in the x direction, we do have an acceleration. It's due to mg sine theta, and I can set up a formula of the force, mg sine theta, divided by m. That's the inertia. The m's cancel. If this surface is frictionless, the acceleration will be g sine theta. All right, I can put numbers into that, and that tells me that the acceleration along the incline, 4.90 meters per second squared. Now, of course, in Chapter 5, we're going to come back, look at the same mystery box, and we're going to introduce friction. And then that will change somewhat. Now, in the perpendicular direction, we have no acceleration, and that means that n is equal to mg cosine theta, and we can calculate those forces. mg is still 98 newtons, if you remember, but mg cosine theta is 84.9. So the normal force is reduced, and some of the gravitational force is creating an acceleration. And again, when we come back and look at friction, we'll add those forces in, but this is such an important diagram too, getting us used to using inclines. And I think that's it. That's everything we want to talk about. So I think I am going to, I'm going to just leave it there to stare at. So any questions at all about any of the stuff we've talked about? We are really into the physics now. Stop by office hours. Let's take a look at whatever questions you guys have.